idea. So we start with a G, a compact Lie group. And we would like to understand the category of G cohomology theories. So we would like to understand the invariants which are going to take into consideration the G action. So a model for G cohomology theories is given by the category of G-spectra with the stable model structure. So the aim is to understand this category. But now this is quite complicated. I mean, we all know this is quite complicated. Well, for the trivial group, this is just the category of spectra, and the endomorphism ring of the unit is already very, very complicated, right? So there's no hope to actually understand this category as such yet. So what are the complications really in this situation? Well, the complications come from two sides. One of the sides is equivariance. So the fact that we have a G and there's some internal group action. And the other side, which is also visible in here, comes from the torsion. So the fact that we're really looking at cohomology theories with values in abelian groups. So this part contains a lot of interesting information, whereas this one, well, let's start by simplifying this thing. So let's work over Q. Let's tensor everything with Q. So instead of talking about cohomology theories, let's talk about cohomology theories which take values in rational vector spaces, but they are still having the G action. So this is something which I'm going to call, this is modeled by G-spectra, rational G-spectra. So this gadget is still remembering a lot of this information that we would like to analyze, but it's much, much simpler. It doesn't have any torsion anymore. So what do we mean by really understanding this category? Well, we would like to be able to take a look at it. So this is happening in topology. We would like to be able to take a look at it from the algebraic point of view. So we would like to be able to get another model for the homotopy category of this. So another model for G cohomology theories with rational coefficients. But the model which is going to live in algebra, so it's going to be much easier. So I'm looking for something here, some model structure, some category with a model structure linked to my category by a zigzag of Coulomb equivalences. So this is what we mean by looking for an algebraic model. We're looking for an algebraic category which is going to model the same homotopy theory as G rational G spectra, but it's going to actually be living in algebra. So you can think of it, the building blocks are going to be chain complexes of Q modules, or graded Q modules, or something of this kind. So let me make it a little bit more precise. So there's a conjecture of John Greenlee's, which says that for every compact Lie group G, Lie group G, there exists an algebraic model. Well, how is it going to be given? There exists an abelian category, so this is an abelian category, of injective dimension equal to the rank of G. So not too complicated, such that if I take a look at the differential objects in this category, together with the homology isomorphisms and the rest of the model structure, I'm going to get a Coulomb equivalence to the rational G spectra. Okay? So we want to find an algebraic model for any compact Lie group G. And today I'm going to tell you what is the state of this conjecture, what are the methods that we're using to prove the results, and what is the general hope for the future. So let me start with, well, the most basic situation. So when we have a trivial group. When we have a trivial group, there's a theorem of Shipley which says that, well, if you take spectra, rational spectra, this is going to be equivalent to the category of chain complexes of Q modules. So I didn't tell you what this gadget is. So this is going to be a left Bousfield localization of the category of spectra. I'm always thinking about orthogonal spectra. Left Bousfield localization at what we call the rational sphere spectrum. So this is a gadget. This is a Moore spectrum for the rational numbers. So it has a property, this is the important thing, that if you smash anything with it and take homotopy groups, it's like you took the homotopy groups and tensored it with Q. Okay? So it really is tensoring your cohomology with Q. You're going to get cohomology theories with values in rational vector spaces. So what do I mean by left Bousfield localization? This is a change of a model structure where the weak equivalence is now, a map is going to be a weak equivalence if F smash SQ is a pi star iso. So it's a stable weak equivalence. And the cofibrations is as they were before. So let me point out that this is going to turn out to be a very powerful result. This is going to be our only way to move from topology to algebra. And every time we're going to be looking for an algebraic model for more complicated groups, we're going to use this theorem towards the end. We're going to use this theorem towards one of the last steps to be able to move from the topology to the algebra. So before I get into more complicated groups, let me give you some background. So there's a lemma of Tom Deek, which says that you have an isomorphism of rings. So I'm going to take this is a different A than it was before. That was the curly A. This is a straight A. This is a rational Burnside ring. Okay? Rational Burnside ring for G. What is it? Well, it is the endomorphism ring of the sphere tensored with Q, or in the other hand, it's the endomorphism ring in this particular category, the localization, or it is also the endomorphism ring of the rational sphere. So the lemma says, this is the part of the lemma, it says that you have an isomorphism with the ring of function, continuous functions from, let me say that, from the space of conjugacy classes of subgroups of G, but not all subgroups, such that they have finite index in their normalizer. So that means if I take the normalizer of the subgroup mod the subgroup, I want this to be finite. Okay, this is G. The topology is the quotient topology of the Hausdorff topology in here. This Q is with discrete topology. And here, I mean continuous functions. So why did I bring up this lemma? Well, I'm interested in idempotents of the rational Burnside ring. I'm going to use them later on to split the category of rational G-spectra. So I'm going to use this isomorphism of rings to be able to take a look what those idempotents are. So let me give you first an example of this gadget. So let's suppose that G is finite. Then all subgroups of G are going to have the finite index in their normalizer. And this thing is just conjugacy classes, so coproduct conjugacy classes of the subgroups of G. Finitely many, okay? If I have more complicated G, well, let's say G is S of 3, what can happen there? Well, I'm going to have and this time I'm going to draw you. I'm going to have a point corresponding to SO2. SO2 is a maximal torus in SO3. I'm going to have points corresponding to dihedral subgroups, which are actually going to converge to O2. So D4, how do I number them? Okay, I number them like this. So D4, D8, D16, so on. I'm going to have some special subgroups as well. So the sigma 4, the symmetries of the cube, the symmetries of the tetrahedron, the symmetries of the dodecahedron, and SO3 itself. Okay? Those are just separate points. This is the only convergent point. And those are these. So dihedral subgroups, finite dihedral subgroups converging to O2. Notice that I didn't put D2 here on the list, because in SO3, D2 is actually conjugate to C2. It's every reflection is actually a rotation in a different axis. So it's already actually hidden in here. C2 doesn't have a finite index in the normalizer. It's not going to appear on itself. So all the subgroups which don't have the finite index in the normalizer are hidden somewhere in this picture. So for example, if you think about idempotents, and I brought the, what are the idempotents on this picture? Well, okay, I didn't tell you what the, so let me just go back for a second. Let me just give you a brief, you probably already figured that out, but idempotents of the rational Burnside ring, so some E which is square into itself, are going to correspond to open and closed subsets of this space. Why? Well, if I have an idempotent, it's going to be an idempotent continuous function, so it's going to be continuous functions with just values in 0 and 1. So I'm just looking at what is sent to 1. So I'm just looking at the support of the function. And because this was a discrete space, well, the support of this function is going to be an open and closed set in this, in Fg mod G. So what are the idempotents? Well, the idempotents on this picture, every point is going to be an idempotent. On this picture, I can choose this as an idempotent, and this is going to be called ET. This is an idempotent picking the maximal torus. And it's actually going to have information, it's going to remember information about all its subgroups. I can take, well, if I'm taking O2, I need to take something, everything converging to it from some point, and those guys can go separately. So this is an idempotent splitting, let's say like this. This is an idempotent splitting. And every time I'm going to have such a splitting, I'm going to be able to split the category of rational G-spectra. So what do I mean by that? So, okay, I can do it here. So notice that so far we're talking about homotopical idempotents. So this is an idempotent at the level of homotopy. But we can actually define what we mean by idempotent applied to SQ. This is going to be a certain homotopical limit of a diagram of SQ, idempotent SQ, and so on. And if I define it this way, I can define a category I can localize the category of G-spectra at some idempotent. And it's going to turn out that this category models the homotopy theory of spectra, of G-spectra, which have geometric isotropy related to this E. It's not going to be exactly the support of E, but it's going to be related to E. It's going to be everything in the support of E together with all the things which have quatorial inclusions into things like this. So you should think about, even though E here is just SO2, if I localized G-spectra at ET, it's going to remember the maximal torus and all its subgroups, okay? Not only the maximal torus. So now let me tell you, why did we talk about this? Yes. So why did I tell you about this? Well, every time I'm going to have an idempotent of the rational Burnside ring, we know that the idempotent splits the homotopy category. I lost the white chalk. So if E is an idempotent in rational Burnside ring, then I know that the homotopy category of G-spectra, rational G-spectra, is really going to be E of it cross 1 minus E of it. So this is not that difficult, but there's a theorem of Dave Barnes which says that you can actually upgrade this splitting to the model categorical level. So what do I mean? I mean, if you take the category of G-spectra, and this time let me put the notation as I was using it before. So rational G-spectra is equivalent to the guys which are localized at an idempotent and the guy which is localized at everything else. Okay, I can always do this finite splitting. So now I have this tool of splitting the complicated category into easier pieces. So the general approach is to use the two tools that I have given you, so that you take the category of rational G-spectra. What do? Well, you split it using the idempotents. You try to simplify it as much as you can. And what do I mean by that is remove the equivariance on the outside. That's going to become a little bit more clear in a minute. And then use Shipley's theorem to move to algebra. You might need to simplify this algebra later on, because the gadget that you might get here at the end of this process might be really complicated. But this is the basic idea that we want to follow. So now that we have this approach, well, let's see what happens when we take any finite G. How do we get an algebraic model? So we start with rational G-spectra. We use the splitting result of Barnes. You get a product over conjugacy classes of subgroups of G. Because my space was finite, I could just split them into those little pieces. So idempotent for every of the points. And now I can work with one of those gadgets on its own. So I take one of those gadgets and I try to simplify it further. So what do I want to do? Well, I want to finally get to a stage where I'm going to have equivariance on the outside. So what I'm going to do, I'm going to, well, first restrict to the n spectra, because, let me just write it down. N spectra, when n is the normalizer of H and G, of H and G. And then I'm going to take H fixed points, okay? So this process is going to land me up in what we call W. W is n mod H. Well, let me just write it down. This is going to be equivalent equivalence, the first one. This is going to be equivalent equivalence, the second one. Because I restricted myself to such a small piece, taking H fixed points is going to remember enough for this to be equivalent equivalence. So at the end here, what is this? This is idempotent at 1. So this is like thinking about weak equivalences are underlying weak equivalences. So I disregard the W group action. So if I'm considering this category with this model structure, this is actually equivalent equivalent by the equivalence of categories with the spectra with a W action. So I can move the equivariance on the outside. I have spectra with a W action. So what do I do now? Well, I knew how to get from spectra to algebra, to chain complexes of Q modules. Now I can upgrade the Shipley's theorem to work it with W on the outside. I wouldn't be able to do it if the W was still involved in building my category. But since I'm considering W objects, and W is a finite group, the Shipley theorem, which is no longer here, upgrades to considering equivariant objects in any category. If I had equivalent equivalence and W objects in both sides, that actually prolongs nicely. So this is going to be equivalent equivalence. And this gadget is just chain complexes of QW modules. So what we've learned here is the theorem that the algebraic model, let me just spell it in words. Algebraic model for G finite is a product over conjugacy classes of subgroups of H of chain complexes of QW modules. Okay? That was easy. That was just the finite group. What do we do in more complicated situations? So the next one up is, well, we're not going to do all of them like one by one, but the next one up that we're going to consider is going to be the case where G is a torus, any rank torus. And it's a new theorem by Shipley, well, Greenlee's Shipley, I should get it alphabetically. Which tells you that if T is any torus, any rank torus, then there exists an algebraic model for T. Yeah, let me just stay it like that. Well, first of all, this algebraic model is quite complicated. I would say it's very complicated. But how do we get to this algebraic model? Because everything I told you so far does not apply. Why it doesn't apply? If you think about a torus, what is the rational Burnside ring of a torus? It's just a point. I don't have any idempotents to split anything. So what do? I have just this very complicated category. What do? What is my first step? And it turns out that we're going to get a different kind of splitting. But we're still going to split our category into simpler pieces. So let me tell you the idea of the proof for just SO2. That's already going to be complicated enough. What other kind of splitting I can get on my category? Well, there's this fantastic result which tells us that a sphere spectrum it's actually a homotopy pullback of a diagram. Let me write down the diagram first. It's analogous to the arithmetic square for integers, but what are the gadgets in here? I take a family F. This is a family of all proper subgroups. Okay, in our so all finite subgroups of SO2. I can construct EF out of it, and then DEF is just a dual. So the functions should probably put classes here. EF plus into S naught, so the sphere. And if I have EF plus, I can map it down to S naught, and I can take the cofiber of that, homotopy cofiber of that, and that's what is called the E tilde F. Okay? A splitting of a sphere. So what did I do? I put some information in here. This part is going to remember the geometric fixed points for the torus. This part is going to remember the geometric fixed points for all its finite subgroups. And this part is going to tell me how to glue those two things together. So if I want to understand the category of G-spectra, where G is a torus, so the category, I was using the notation T-spectra. Okay. So the category of T-spectra is really the category of S modules in somewhere. If I split it S, I can move down now to the category of modules over this diagram. A diagram of ring spectra. Okay? I didn't tell you precisely what that would mean, but there's a way to make it formal. This is not going to be quite a equivalent equivalence yet, so we're not going to be able to get the splitting yet. But what we're going to do, we're going to first observe that this left adjoint is homotopically fully faithful. So what that means is that if I take the homotopy category of this part, it's going to very nicely sit in the homotopy category of this part. But this gadget is going to be way too big. So what we're going to do, we're going to force it to be smaller. At the model categorical level, we're going to force the model category to get me the homotopy category, which is going to be smaller. So what we're going to do, we're going to use what is called the cellularization principle. I'm going to start abbreviating your Brooke. So Greenleaf and Shipley, which is going to tell me that if I figure out how this homotopy category is going to be built, and we know how it's going to be built because I have a set of small generators, or compact, which is going to be building my homotopy category. If I move them by F, and do the cellularization, the process which is called the Rydberg localization, then this becomes equivalent equivalence. So let me just write it down. F of k cell, this is the process of Rydberg field localization, or also cellularization. Of this gadget, this is going to be equivalent equivalence. Okay, I just forced my too big category to be a bit smaller, to be as small as I needed it. Okay, but this is kind of a splitting. What I can do now, I can look at one of those gadgets and now take the T fixed points. It's going to turn out that taking T fixed points, where T is SO2, it's going to be behaved nicely. So I'm going to get equivalent equivalence with Let me just put it like this. But now this gadget lives in spectra. Previously, I still had an equivariance in my underlying category, but now I live in spectra. And again, the complications here are actually hidden in this very complicated ring object. But that's OK. I can still apply Shipley's theorem, which is actually monoidal, which is going to tell me that you have modules over some ring. That's fine. You can still transfer them to the world of algebra. And let me just call it theta. And this is going to be happening. Well, I don't really want to say that. Let me just say in algebra. This is going to be equivalence. This is going to be, again, complicated, but we're going to be able to simplify it. And at the end of the story, each of those pieces is going to give us a module in algebra over some algebra which is going to be homotopy equivalent to this one. Not very difficult. There's this cellularization which is dragged on for the whole process, and only when I'm in algebra I'm actually going to bother about recognizing what it does to my things. So at the end of the process I can give you what the answer is. The algebraic model is going to be given by a diagram of rings, which is usually denoted like this. So this is a diagram of rings. So I'm considering modules over this, plus some conditions. This gadget is an infinite product of QC in degree minus 2. This gadget is taking this thing and doing, inverting the first C, the second C, up to Cn, and taking the colimit of those over n, this ring. It looks very complicated, but it's actually manageable. The conditions are also manageable. So you get an information on what your rational T spectrum is, really, by looking at the algebraic model. And it actually can be used to define some new cohomology theories, as John did quite a while ago. The conditions that I was talking about, the diagram comes in really from looking at every piece separately. The conditions which show up are coming from the cellularization here that I'm going to recover at the end of the process. I'm going to tell you what exactly this cellularization is going to mean. So let me tell you what can we do in even more general situations. Like, what can we tell, what can we do if we can get an algebraic model for general G? What's the situation for general G? Well, in this, I'm coming up to our recent work. So first of all, a little lemma that for any G compact Lie group, there exists an idempotent ET in the rational Burnside ring, which is really corresponding to the maximal torus and all its subgroups. So supported on T. So if I have that, I know that for general G, okay, G any compactly, I can split the category of G spectra, rational G spectra, into two pieces, well, at least two pieces. I know I can use this idempotent, so I can split into rational sphere and the rest. And what I'm about, sorry. What I'm about to tell you is that we can actually model this whole big chunk for any compact Lie group G. So we do it in 2 steps. So this is Barnes, Greenleaf, and me. So there exists an algebraic model for this chunk corresponding to the maximal torus. If I'm looking, I specifically change the notation. Very good, very good. This is 1 minus this. Thank you, Agnes. Yeah. So we can do this. We can provide an algebraic model, provided that t is normal in n. So I'm going to use the notation w for n mod t. How are we going to do that? Well, we're going to link our situation with a very nice algebraic model that there exists for the torus. So we're going to be able to recognize that since the torus and all its subgroups are sitting very nicely in the group N, they're somehow all sitting in the same way in the group N. I can look at the chunk of the torus and all its subgroups, and then I have just to figure out what is this W doing to the whole chunk together. So the idea is that the algebraic model is really given by the algebraic model, let me just call it A for the torus. This is algebraic model for the torus with the outside W action. Okay, W objects, W is a finite group, W objects in this algebraic model. But we can do more. What if my maximal torus is not sitting so nicely in the group? We can still do this. So we can still provide an algebraic model for LET, SQ, G-spectra. So for any G. Well, how are we going to do that? Well, the idea is to take the piece that you're interested in, restrict it to the situation where you know what to do, so restrict to this previous situation. This is not going to be quite a Coulomb equivalence, but that's okay. It's again going to be a situation as I was describing there. This category is going to be generally having much bigger homotopy theory. But this functor, the restriction functor at the homotopy level, is going to be fully faithful. So I can do the same trick as I was doing before. If K is a set of compact generators, I can celerize with the image of K. And once I do this, this becomes a Coulomb equivalence. So the idea now is to use the algebraic model for this whole gadget, move all the way down to the algebra, and then at the end recognize what difficulties this celerization is going to give me. Okay? We're going to be doing this in algebra, so the situation is going to be much easier. So this is one part of what we can do for general G. The other part what we can do for general G, there are certain subgroups in, doesn't matter how big G is, there are certain subgroups, oh no, I erased the picture, which are really going to be behaving as if they were finite. So there was a nice picture here, which had those subgroups sigma 4, A4, A5, and SO3, and those were subgroups in SO3. And those were idempotents for those subgroups in SO3, in the rational Burnside ring for SO3. Each of those had their own idempotent, and actually each of those had, finite index in their normalizer because they appeared here, but also there was no subgroup which would be cotoral inside them. So there was no subgroup K such that, this is our choice of ages, such that H mod K was a torus. So in other words, this subgroup was living on its own in the rational Burnside ring. It was not carrying along itself any subgroups. This quatorial inclusion means that the information for H, the idempotent which is picking up H, is going to also drag the information about K. This is what happens for the torus. A torus and any finite cyclic subgroup, this is exactly the torial inclusion. So those subgroups, from the viewpoint of homotopy theory, are going to be really behaving as if they were finite. I can produce exactly the same algebraic model for the part which is localized at this idempotent, the part which is localized at this idempotent, and so forth. So I know already how to do certain things for a general G, although, of course, the things are getting much more complicated. If you take a look at the dihedral part in O2 or SO3, there's some topology going on. And this is just the beginning. Higher up, there's going to be topology going on, and also some quatorial subgroups and interplay between those things. But we're getting there. I think we already know what the algebraic model, what the abelian category for any group G should look like. So far, the description is quite complicated. But to prolong it to Coulomb equivalences, I think there's still some time to go. I guess I wanted to tell you something about the monoidal structures, but I think I'm out of time. Is that correct?
There's 5 more minutes for.
Okay, so maybe I can actually take those 5 more minutes and tell you just the last little interesting bit. So some of you in half an hour before my talk were listening about the equivariant operas. So let me link to this a little bit. So we do have in 2 situations where G is finite and where G is SO2, the algebraic model for those 2 situations is symmetric monoidal. It's quite dangerous to say things like that, but let me explain what I mean. I mean all the equivalent adjunctions that I'm going to use to get to the algebraic model are going to be symmetric monoidal. So what would that mean? That means that if I have G-spectra, and here I have algebraic model, I have a Coulomb equivalence, which extends to the Coulomb equivalence for ring spectra and algebras. And also, if I pick my ring and I consider R modules, I get a Coulomb equivalence with, let me just call this theta of R. This is the image of R in the algebraic model. So I'm going to get those Coulomb equivalences. So now the question is, okay, what happens with commutative things, okay? So commutative ring spectra. So first, what do we mean by commutative, right? There are various levels of commutativity. So commutative ring spectra, depending on which actual n-infinity opera you're going to take, are going to have certain norms. Norms are linking different subgroups norms are maps which are linking different subgroups. What the algebraic model does, in the first step, if you think about the finite group, I'm splitting the category. I'm just separating each information into as small pieces as I can. I'm treating every subgroup separately. I'm killing all the norm maps. If I even had any norm maps, I'm killing all the norm maps. What I'm saying here is that for genuine commutative ring spectra, we're not going to be able to see anything Coulomb equivalent in the algebraic model because of this first splitting result, which is killing all the norm maps. Norm maps are homotopical information, so if I had a Coulomb equivalence, that would be preserved. But there's a theorem, and this shouldn't be surprising. This is, again, Barnes, Greenleaf, and me, that if you put naive commutative ring spectra, so the ones which do not have any norms, then you get Coulomb equivalence with commutative algebras. And if you think about it, on the algebraic side, that there's no space for anything more commutative than commutative algebras. So it's not a surprising result. It's something that I guess was necessary to do it. But a sanity check, let's say, that what you can recover on the other side, you really do. Okay, there's no chance to recover anything more. For that, the algebraic model would have to have a different passage, but everything that you actually can recover, you do on the algebraic side. So thank you. Say again.
So if I work with S1 with the torus, is it possible that I can maybe recover some sort of norms, just?
I think with the torus is going to be better because yes, that's true. That's true, and I think this is possible for the torus because what are going to be the norm maps for the torus? There's not going to be any norm map going from the torus into any finite subgroup because this is infinite index, right? And the splitting that I was doing, it's maybe even, no, it's not on the board. So the splitting that I was doing, I was looking at the DEF plus, which was remembering all the finite subgroups together, and the torus separately. So I think there is a chance that there is going to be some information still preserved, but I haven't thought about that. I don't know, Brooke, have you thought about that? Yeah, but that's a very good question, yeah. I don't. Looking at Angelica, I was like, yeah. I don't know, Brooke, you like? Yeah, it's like so sorry.
Magdalena again?